Although it is useful to know about different types of main effects in general, the topic often comes up for students in the context of comparing one or more of the approaches that I just talked about in R to the SPSS univariate ANOVA function, called UniANOVA, UNIANOVA, available via the menus Analyze, General Linear Model, Univariate. This SPSS function, very commonly used, defaults to type 3 main effects with contrast coding. I will illustrate. This is an SPSS interface, and I've loaded in the robots dataset from my CSV file. I'm not showing you how to load the CSV file, but the point is that it's here in SPSS, and I can go to the Analyze menu, choose General Linear Model and Univariate to get the UniANOVA function that so many people use. You get a dialog box like this. Put the dependent variable or response variable in this box, and the two predictors that you expect to interact in this box, labeled fixed factors. And the result is output like this. Here I have an ANOVA table that resembles the ones that we were looking at in R. Up here, there's also some useful descriptive information about the relative sample sizes in the various cells, which should be a clue to you how much of a difference the type of main effect would make at all. Here, the sample sizes are reasonably close, so all three types of main effects should be pretty similar. In this ANOVA table output, it says type 3 sum of squares right here in this heading. So that's another clue that SPSS is using something like type 3. It doesn't indicate that it's type 3 with contrast coding, but that is what SPSS means by type 3. Here is the R output from two approaches. The default version that I recommended was type 2, which is the default in the capital A ANOVA function from the CAR package. And if I plug in this same regression model, material and transport interact and price is the response variable, then I get this ANOVA summary table that has some variance explained by each main effect and the interaction. In R, I also showed you the contrast-coded type 3 version, which set up contrasts by encoding each value of material and transport as negative 0.5 or 0.5, so that 0 would fall precisely between the values of material and transport. Then I called the capital A ANOVA function from the CAR package with this full regression model, and type specified to 3, and I get this ANOVA table output, where the interaction hypothesis test is precisely equivalent to the version up here, because they're coming from the same regression model that has the interaction in it. But the main effect hypothesis tests are slightly different from the ones up here, because these main effects, where material has an F value of 26, for example, are based on variance explained in a model that does not include the interaction. Whereas these main effects down here are based on the variance explained in a model that does include the interaction, and where the effect of material is estimated at the precise midpoint of the two values of transport, and its F value comes out to 25 rather than 26 in this case. The conclusion you would draw would be exactly the same, but the result appears to be slightly different, and it's useful to know why. Here's the SPSS output overlaid. You can see that this F value, 25.066, precisely matches this F value from the contrast-coded type 3 version that we did in R. I'm showing you this so you don't get confused if you do it this way in R like I recommend, and then compare it to SPSS and see that the F statistic is ever so slightly different. If you want it to match SPSS exactly, then you'll need to do the contrast-coded type 3 version, where you set up contrasts that are perfectly symmetrical around 0 ahead of time, and then plug them into the capital A ANOVA function with type set to 3.